This is the last model, okay, the random effect model. It is the last model we are going to use to explain how to deal with the unobserved heterogeneity. Okay. So what random effect does is this. It assumes that the UI, the unobserved factor, they are identically and independent distributed, or independent and identically distributed. Okay. They are also, the UI, they are not correlated. This is very important. Okay. Now, if you can see, fixed effect assumed that it was correlated. If you can remember, fixed effect, it assumed that it was correlated. I just want to show you very briefly that assumption. Okay. It assumes that it was correlated. It was correlated with something in the error term. And that is why it tried to now use the transformation approach to kill those that don't have time. So that everything that is here is the time factor that is here. Okay. Now, random effect is different because random effect assumes that there is no correlation between the UI and the XI. That is between the unobserved heterogeneity and the independent variable. It assumes that they are not correlated, which means that the covariance between them is 0. And so if they are not correlated, then fine, let me let it go and be in the compose error. Let it stay in the compose error. But a fixed effect, in fixed effect, the UI is treated as a constant. Okay. The UI is measured as a constant. If we assume that the covariance between the UI and the XI, okay, or the uncorrelation between them, okay, then we won't need the first difference or the fixed effect anymore. Because there will not be any endogeneity. Endogeneity is when the UI is correlated with, the XI is correlated with one of the UI. So when the error term is correlated, then with the others, then you see that there is endogeneity. And when you use OLS2, it will lead to serial correlation of the errors. And that is why we use the random effect model. Now, the random effect model is the GLS or the feasible GLS version in a panel data model. So when we jump from cross-sectional model to a panel model, the battle now has to do with we have a different name. And the different name is not WLS, not GLS, but feasible GLS. But it's not called even feasible GLS. It is properly called random estimated model. Okay. So that is why we use the random estimator. Now, here's where it becomes a little bit technical, so please watch. The covariance between the unobserved factor and the error term, and the covariance between that same unobserved factor and error term is equal to 0. The covariance is equal to 0, okay, which means that there is no autocorrelation. Now, this symbol here means that when you take the variance of the UI, the error term, which is the unobserved factor, and then you also take that one and the variance of the actual error term, okay, where T is equal to S, which means that the number of times are not the same, they are different times. Okay. Then we can now say that there is no autocorrelation. That's it. But this autocorrelation can be handled in FGLS. I've said that before. Okay. In panel model, the FGLS assumes the nature of random effect. So what is the actual panel model? Again, as always, we remember the general model. The general model is what you see on the screen. Okay. Let me just pinpoint it so beautifully so that at least somebody will understand where we are coming from. So let's take let's take this panel model. And we're going to rewrite it as if it is now a random effect model. Well, when you do that, this is what it becomes. Nothing changes. Remember we said that the epsilon is IID. The UI2 is also IID with the zero mean and that variance that you have. So the way you model the random effect is not too different. However, there is something small. These kind of app thing, sometimes it can be very interesting. Okay, is a random effect estimator, is it sufficiently efficient? Is it efficient? Does it have a high convergence? Well, once you have corrected for the serial correlation, the random effect will be more efficient than the pooled OLS and the fixed effect or the random. Once you've corrected for the serial correlation, how do you write this? Let's write the equation now for the transform random effect estimator. So you get YIT minus theta YI equals to, you apply everything here to theta. Now you're going to understand theta very soon. So once you do that, this becomes the random effect estimator. Mind you, we don't know what the theta is yet, but this is what we know. If theta is 0, then everything in this bracket is going to be 0. So what it means is that if theta is 0, we are going to get back everything. Just check. If theta is 0, we'll get back this same equation. The same equation is gotten back if theta is 0. And so when theta is 0, it means that, and we fall back to that equation, it means that we are now in the world of OLS. That's what it means. It means we are no longer anything except OLS. If theta is 1, theta is between 0 and 1. If theta is 1, then the random effect and the fixed effect are the same. But in real life, theta is between 0 and 1. Okay, so random effect is never OLS or fixed effect. What is theta? What is theta actually? You see this in several packages, but what is it? Well, we've already said that when theta is 0, we fall back to our OLS. So how do you get this random effect? Well, the first thing is this. If you look at the terminologies, you need to find the values of the variance of the error. Okay. You need to also find the values of the variance of the other error, and then get the fixed the theta cap using OLS or fixed effect. Once you got that, you substitute that and then use OLS on the transform model, which is this very one. So this is obtained and it's capped. That is why it is what it is. So that is the basic. So when somebody asks you what is the basic of the random variable, random estimator, this is it. This is the basic equation of the random estimator. Now, the assumptions of the random model is what you see here. I'm not going to go through any one of them because they are very similar to all other previous ones. So let's go and now model the random effect. Okay. Let's go and model the random effect in their application.